Welcome to the tutorial on simulation of binary multiplier using Multisim. So what is a binary multiplier? A binary multiplier is a combinational circuit used in digital systems in order to perform the multiplication of two binary numbers. So we have the two binary numbers 0 and 1. And when we multiply 0 with 0, we obtain a 0. 0 with 1 is equal to 0. 1 with 0 is equal to 0. And 1 with 1 is equal to 1. So this is equivalent to multiplication of decimal number 1 and 0. So when you multiply 1 with 1, you yield a result 1. Otherwise, the result is equal to 0. There are numerous applications of the binary multiplier, most widely used in the field of digital signal processing to perform various algorithms. In commercial applications like the computers, mobiles, high-speed calculators, and some general purpose processors will require binary multipliers. So this binary multipliers are similar to the multiplication of decimal numbers. So binary multiplication will follow the same process for producing a product result of the two binary numbers like the one we have seen here. So we can say that binary multiplication is much easier as it contains only zeros and ones. So these are the four fundamental rules for binary multiplication that you need to keep in mind. Next, binary multiplier, array multiplier, or a parallel multiplier. So we can name the binary multiplier as an array multiplier or as a parallel multiplier. To define a binary multiplier, it is a combinational logic circuit or a digital device which is used for multiplying two binary numbers. The binary numbers can be of any bit. The two numbers are more specifically known as the multiplicand and the multiplier, and the result is known as the product. So you can see here B1 and B0 are of 2 bit. A1 and A0 are of 2 bit. So basically you're multiplying A with B. The first term is the multiplicand and this is the multiplier. The end result that you obtain is called as the product term, which is represented as P0, P1, P2 up till P3 in this particular example. So as I specified earlier, the multiplicand and the multiplier can be of various bit size. The product bit size depends upon the bit size of the multiplicand and the multiplier. So the size of P will depend upon the size of A and B. The bit size of the product is equal to the sum of the bit size of the multiplier and the multiplicand. So if you see here, you have the result, that is the product P0, P1, P2 and P3, which is of 4 bits. So this is equal to the sum of the multiplier, which is 2 bits, plus the multiplicand, which is 2 bits. So 2 plus 2 gives you a result of 4 bits. So that is why we have the product to be equal to P0, P1, P2 up till P3, which is of 4 bits. Now as mentioned earlier, binary multiplication method is same as that of the decimal multiplication. So binary multiplication of more than 1 bit numbers will contain 2 steps. So the first step is a single bitwise multiplication, which is known as the partial product, and the second step is adding all the partial products into a single product. So here you can see in this example, when you multiply A0 with B0, you obtain one term. A0 B1, you obtain another term. So this first two terms that you obtain is called as the partial product 1. Similarly, when you multiply A1 with B0 and A1 with B1, you obtain the next set of partial products. When you add the two partial products, you get the final product term or the final result, which is represented as P. Moreover, each successive partial product is shifted in one position left. As you can observe here, there is an X here indicating that it is shifted one position left relative to the preceding partial product before summing all the partial products. So if you had to multiply, say, 3-bit numbers, then you would have obtained few more terms wherein at each partial product would be one left shift relative to the previous one. So in general, I can say that multiplication uses n shifts and adds to multiply n-bit binary number. The combinational circuit implemented to perform such multiplication is called as an array multiplier or a combinational multiplier or a parallel multiplier. Now, if you are to realize these binary multipliers or array multipliers or parallel multipliers using gates, then you can realize the partial products or the single bit products by using AND gates. But to add these partial products, we will need full adders, half adders. The schematic design of a digital multiplier will differ in size. That is because if you are going to multiply only 2-bit numbers, then you will require 4 AND gates to implement A0, B0, A0, B1, A1, B0 and A1, B1. Whereas for the summation, you would probably require only half adders. Whereas when you go for the multiplication of higher binary bits, more number of AND gates, and you will require both half adders and full adders. So before we proceed further, we need to understand what are the different types of binary multipliers that we have. So we can have a 2x2 bit multiplier. We can have a 3x3 bit multiplier. We can have a 4x4 bit multiplier. So let us discuss each one of this. So first we have the 4x4 array multiplier. So the block diagram clearly shows that we have the two inputs A and B. These inputs A and B, one is the multiplicand and one more is the multiplier. So this A is a 4-bit, B is also a 4 bits, and at the output you will get a total of 8 bits. That is because as we have seen earlier, if you want to know the size of the product term, it will be equal to the size of the multiplicand plus the size of the multiplier. So that is why you obtain here it as 8. So here is one example which they have shown, wherein clearly they are telling how we can perform the multiplication of 4x4 bits. So this multiplier can multiply a binary number of 4-bit size and give a product of 8-bit size, because the bit size of the product is equal to the sum of the bit size of the multiplier and the multiplicand. So the maximum number it can calculate is 15 cross 15, that is equal to 225. And you can also evaluate the number of bits from the maximum output range. Suppose we are multiplying A3, A2, A1, A0, and the multiplier is B3, B2, B1, B0, then the product term will be P7 to P0 for the 4x4 multiplier. And here we will have a total of 4 partial products, and we need to add these partial products in order to obtain the product terms. And these can be added by using the 4-bit full adders or single bit adders, that is half adder and a full adder. So let us look into the design of single bit adders, which is very much complicated in corresponding to the lower array multipliers. So here you can see that I have a 4x4 multiplier which is implemented using the AND gates and the adders in order to add the partial products. So I have the term A0, B0, A1, B0, A2, B0, A3, B0, A3, B1, A2, B2, A2, B1, A1, B1, A0, B1. So you can see that these terms, these product terms that are obtained are nothing but corresponding to the partial product terms obtained in the multiplication process. That is, these terms that are obtained. So when you want to combine these terms and perform the addition, you will have to make use of adders and full adders depending upon the number of terms that are involved in the addition process. If you're adding 2-bit numbers, then you would require just a half adder, whereas if you're adding more than 2-bit numbers, say 3-bit numbers, you will require a full adder. So that is why you can see that in this particular array multiplier we make use of both half adders and full adders. For our simulation using the Multisim, we will try to implement using the 2x2 multiplier so that it is easier for us to understand. Moreover, you can implement a higher array multiplier with a simple understanding of the 2x2 multiplier. But before going to 2x2 multiplier, we need to see how a 3x3 multiplier will be implemented. For a 3x3 multiplier, we need to multiply two numbers having a bit size of 3, and the bit size of the product will be equal to 6, and the maximum range of this product will be 7x7, that is equal to 49, and this can be accommodated in 6 bits, which is the size of the output product. So here we will have 3 partial products which will be added using 2 methods. Either you can add the partial product using 3-bit full adders, or you can make use of individual single-bit adders. Next, moving on to the multiplication of 2 bits, because this is what we are going to implement. So here this multiplier, as you can see, makes use of two numbers having a bit size of 2, that is A is of 2 bits and B is of 2 bits, and the product will be of the size which is equal to the sum of the bit size of the multiplicand and the multiplier, that is 2 plus 2 equal to 4, and the maximum range of its output will be equal to 3x3, because 2-bit numbers can range from 00 to 11, and 11 in decimal corresponds to 3. So we can accommodate a decimal number 9 in 4 bits. So it is another way of finding out the bit size of the product. So here you can see I have tried to solve and show you how many partial product terms that you will get and how many product terms that you will get. So this is the multiplicand, this is the multiplier, these are the 2 partial product terms, and these are the final product terms. Now if I want to implement a 2x2 multiplier using single bit adders, then I will make use of AND gates, because I need to implement the partial products. So I have 4 partial products here: A0, B0, B0, A1, B1, A0 and B1, A1. So these are the partial products that I have which I'm going to implement, and then I need to perform the addition. For the first term, you have A0, B0 directly yielding the term P0, so that I can obtain P0. Whereas for the second term P1, I need to add B0, A1 and B1, A0. So B0 and B1, A0, that I am going to add using the half adder. The sum I am going to obtain as P1. Whereas the carry of this has to be added to the next half adder. And along with that, I am going to add A1, B1, and you will get as a sum P2 and as a carry P3. So the same thing, realization, we will do using Multisim. So before I go into the implementation using the Multisim, let us verify some of the multiplication product terms for the 2-bit numbers and see what will be the result, so that directly we can come to a conclusion that we have obtained the same result. So in this example, I'm considering the multiplication of 1 1 with 1 1, where 1 1 is the multiplicand and I have another multiplier. So I will name this as A and B. On multiplication of 1 1, I get it as 1. I need to place a shift and the result will be obtained as product terms, whereas the intermediate terms will be named as the partial products. So on performing the addition, I get it as 1 0 0 1, which is equivalent to 9 in decimal. So if you observe here, you can see that A was 3, B was 3, that was giving a result 9 in decimal. In a similar manner, let me consider other examples. I have 0 1 multiplied with 1 1. So I get this as 0 1 0 1x, and the result will be 0 0 1 1, which is equivalent to 3. A and B was equal to 1 and B was equal to 3. So 1 multiplied with 3 will give you a result of 3. Next example, 1 1 multiplied with 1 0. So I get the end result as 0 1 1 0, which is equal to 6 in decimal. So I have A to be equal to 3 and B to be equal to 2. So 3 into 2 is equal to 6. Finally, the last case wherein I will consider the multiplication of all zeros. So here I will get the result to be all zeros. So we need to observe one important thing here is that for the multiplication of 2-bit binary numbers, we will be only using half adders. That is because the number of partial product terms are only 2, and to the maximum we will be getting a carry, whereas if you go for the higher order array multipliers, you will have more number of partial products. So that is why you will also require a full adder. In this particular simulation, I am placing the key space, which is nothing but a switch, so that I can choose between the binary 0 and binary 1 for the multiplicand and for the multiplier. So simultaneously, when the simulation is going on, I will be able to choose the values and observe the output. In this particular simulation, I do not have the half adder which is readily available to me. So what I'm going to do is I will place the full adder, but I will choose only the appropriate sum and the carry bits and convert the full adder into a half adder. In order to observe the output, I will be using the probe. You have various indicators that can be used, but I will choose to use the probe, which will glow when the output is logic 1, and I will be able to easily verify the result. So here what I'm going to do is I'll change the position of the switch to all zeros and observe the output as a first case. So you can see that when I run the simulation, the output will be all zeros because the indicators are not glowing. Now let me change the switch positions to all ones. That is A and B both are 1, and I get the result as 1001, which is equal to decimal notation 9 because I have multiplied 3 with 3. And here it is 10 multiplied with 11, so I obtain it as 0011. For a combination of 1011, I obtain the result as 0110.